Hello, this is Dr. Webb. In the last video, we worked out a couple geometric problems in 2 dimensions, so it's only appropriate in this video if we work out some geometric problems in 3 dimensions. So first problem, this is a problem that really only makes sense in 3 dimensions, and it's that if we have 2 vectors, so let's call a vector v, and let's let its components be, say, a, b, c, and then we have another vector w, and let's let its components be L, M, and N. Then we want to find a third vector, u, which is perpendicular to both of them. Okay, so u is going to be maybe something like this, u, such that it makes a right angle with both v and w. Let's let the components of u be r, s, and t. Okay, so we want to find some u, and there's only going to be one line that's perpendicular to v and w, so there's really only 2 directions, one direction up and one direction down in this picture that you could be going, but we just want to find some u given v and w that'll be perpendicular to both of them. So in the last video, when we talked about dot product, the dot product is one way to detect when 2 vectors are perpendicular to each other. If the dot product is equal to 0, then we know that u is going to be perpendicular to that vector. So really what we want to find is a u such that v dot u is equal to 0 and w dotted with u is equal to 0. And so then that gives us 2 equations. So dot product of v and u, v is abc, u is rst, so their dot product is going to be ar plus bs plus ct. Set that equal to 0. And so this is coming from u dot v equaling 0. And then we want w dot u, so that's going to be L times R plus M times S plus N times T. And so that's coming from w dotted with u equals 0. 0. It's not the 0 vector, it's just 0. Okay, so here are those 2 equations that we got from the last slide. So let's figure out what some r, s, and t could be. Right, so let's start with the first one. Maybe let's solve for r. Okay, and so we have, from the first one I can get minus ar is equal to bs plus ct. To get r by itself, I can divide by minus a, and that's going to give me r by itself. Okay, and then we can plug that into the second equation, see what we get. So we have 0 is equal to L times bs plus ct all over minus a plus ms plus nt. The easiest thing to do here would be to multiply everything by minus a, say. So let's do that. So 0 times a is going to be 0. I'm going to have L times bs, L times ct, plus a, actually it should be minus ams, minus ams, minus ant. Okay, what can we do here? So I want to get s's by themselves, and I want to get t's by themselves. So let's move the s's to the left-hand side, t's to the right-hand side. And so AMS minus LB times S is going to be equal to CLT minus ANT. So actually, let's get all of this in alphabetical order. So let's call that BLS. Okay. And then on the left-hand side, I can factor out an S out of both terms. So let's do that. On the right-hand side, I can factor a T out from both terms. And so we want to find an S and a T such that AM minus BL times S is equal to CL minus AN times T. And so the easiest way to do that would be just to call AM minus BL T, CL minus AN S. And so it just turns this equation into S times T equals S times T. So let's write down how we're doing this. S is equal to CL minus AN. T is equal to AM minus BL. So let's go back to what R then would be. So R is B times S, CL minus AN, plus C times T, AM minus BL, all over minus A. And so the top there I can write as BCL minus ABN plus ACM minus BCL all over minus A. And so then going through here, I have plus BCL and minus BCL, so they cancel. And then I've got a minus A on the bottom and a minus A and an A there, so I can change these signs, cross off the A's. That gets rid of the A on the bottom. And so you can see, hopefully through my scribbles, that R is going to be BN minus CM. Okay, so putting this together, what's the vector U that's going to be perpendicular to ABC and LMN? Well, one U that we can pick would be R, which is BN minus CM, S, which is CL minus AN, and T, which is AM minus BL. And okay, next question. Yeah, so this is what we wrote before. Let's see. BN CL minus AN. So there's our solution right there. Right, so this is not the only vector that's perpendicular, but it is a vector that's perpendicular. And it's probably the easiest one to write in terms of ABC and LMN. That W there should not be KLM, this should be LM. And little typo there. Okay. For the next problem, let's imagine we have two vectors, V and W, and we want to find, we talked before about if given two vectors, they generate a parallelogram, so let's see if we can figure out how to get the area of that parallelogram. So let's let that be V. Again, V is going to have sides AB, have components A, B, and C. We're doing this in 3 space. W, it's going to have components L, M, and N. And then we want to make this into a parallelogram. So there's our parallelogram. So remember, the area of a parallelogram is going to be base times height. That's an H there. Let's at least make this look somewhat like an H. Base times height. Let's let V represent the base. And so our base here is going to be the length of V. Okay. Well, then for a height then, our height is going to be kind of dropping down straight there. So it's kind of perpendicular to V. Well, if you think about it, this is a lot like the problem where we're trying to find a vector that's perpendicular to V that sort of closes up this side. And so if we're making this into a triangle, this vector it's in the same direction as V and goes out up into this point that goes straight up at the end of W. And so this vector right here is the projection of W onto V. And so what's this height going to be? Well, this height here is going to be W minus the projection of W onto V. That's giving us this perpendicular side. And we want to take the magnitude of that vector. So the base vector is just V. The height vector is coming from the magnitude of this perpendicular up vector here, and that vector is W minus the projection of W onto V. Okay, so there's our area. It's the magnitude of V times the magnitude of W minus the projection of W minus V. So if we wrote all this out in components and calculated out the what the magnitudes would be, it would look an awful lot like this. This a squared plus b squared plus c squared. This is coming from the magnitude of V. And then this chunk right here, this is what you get from W minus the projection of V onto W. Okay, so this is what we get in terms of the area. So it'd be nice if we can simplify this. And if you just kind of look at it and squint at it a little bit and then close your eyes and think about it, it should be pretty clear what's going to happen. So you do that. So let's do that together. Let's squint, 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 squint. Close your eyes, clear yourself, think about what it should be. And then when we open, clearly that's what this is going to simplify down to, right? No, actually this takes a fair amount of algebra, which I have swept under the rug. But this is what you can get by working this out. This all will simplify down to this nice formula right here. But if you look at this, Bn minus Cm, that looks familiar. Cl minus An, that looks familiar. Am minus Bl, that looks familiar too. These are all the components, this Bn minus Cm, Cl minus Am, and Am minus Bl. These are the components of the U vector that's perpendicular to V and W that we found. And so then the way this is set up, this is actually the magnitude of that vector U from the first problem. So that's kind of an amazing coincidence. And so we're going to give this vector U a special name. We're going to call it the cross product. So it is, U is going to be called the cross product of V times W. And so this is just using the formula we got before. Now there's another way to get this formula. And it's using this sort of funky derivative. So if you look in this derivative, we have I, j, and k. These are the component vectors. I, j, and k here are the component vectors. I, j, and k. And so then when you work this out, this determinant out, whatever is being multiplied by I, that's going to give you the x component. Whatever is being multiplied by j, that's going to give you the y component. And whatever is being multiplied by k, that's going to give you the z component. Go back and note that for the row in the two other rows in this, the middle row, this is coming from v, and the bottom row, these are the components of w. So it's this funky I, j, and k up on top, and then the middle row you put the components of v in, and the bottom row you put in the components of w. So let's talk a little bit about how to get determinants of 3x3 matrices, which is what we use in this cross product formula. So how to do determinants of 3x3 matrices. So let's give ourselves a 3x3 matrix. Let's say A, B, C, D, E, F, G, H, I. We want to take the determinant of this. So there's a couple different ways to do this. So there's a way where you can kind of pick a row or a column and expand off of that, which you may have learned. I'm going to do this another way. This is the way that I learned it. And so one way you can get this is by, if you copy out the first two columns next to the other column, and then what you're going to do is you're going to multiply down diagonals. And so this diagonal would be AEI, BFG, plus BFG, plus CDH. And so that's the diagonals you get from going kind of downwards. The diagonals you get from going upwards are CEG plus AFH plus BDI. And so you get these two sums, one sum from going downwards, one sum from going upwards. And then what the determinant is going to be is it's the downward sums, AEI plus BFG plus CDH minus these upward sums, CEG plus AFH plus BDI. Okay, so let's go back and apply this to the the funky determinant that we're trying to do to calculate the cross product. So let's see. Let me do. That's decently big now. Okay, so let's erase this out. And so then the determinant we were trying to do had the I, J, and K up on top, then A, B, C, then L, M, N. And so then let's copy these out. A, L, J, B, M. And so then my downward diagonals are going to be BNI plus CLJ plus AMK. My upward diagonals are going to be BNI L K plus C M I plus A N J. And so then if I'm going to take these and then subtract off these, and I want to group them in terms of the i's, the j's, and the k's together. So my I here, I have BNI and then minus CMI. And so this determinant's going to be BN minus CM times I. And then for J, I have CL minus AN. CL minus AN for J plus AM minus BL for K. AM minus BL times K. And so putting this together, so Bn minus Cm times I, that's giving me my X component, Bn minus Cm, Cl minus An times J, that's giving me my Y component, Cl minus An, Am minus Bl times K, that's saying that my Z component is Am minus Bl. And so that's the same thing as we got before. I'm not saying that you have to do determinants like this, but this is how I remember how to do 3x3 determinants. Okay, so what are the algebraic rules of cross products? Because, one way to think about this is in terms of matrices. These rules really come from properties of matrices. So if you've taken something like Math 300, or maybe you've seen this in high school, these will make sense. If you haven't seen those before, if you're planning on taking Math 300 or Math 238 in the future, then you will see these here. You'll see these going in the future, perhaps when you take those classes. So first one, which is kind of weird, if you do V cross W, then that's going to equal, if you try and switch them, well, if you're trying to switch them, you'd actually be swapping rows in a determinant. And when you swap rows in a determinant, you make the sign change. So V cross W is going to equal minus W cross V. Next rule makes a lot of sense. There is a distributive rule. If you do U cross V plus W, this is going to equal U cross V plus U cross W. So this is just a distributive rule. If you want to multiply this by a scalar, so K times V cross W, it's the same thing as crossing one of them. This should be, let's make all of these U's or all of these V's. So let's turn that one into a U. K times U cross W is equal to K times U cross W, or U cross K times W. And the last one, which is pretty weird, but if you know the matrices, this would mean you're making two rows of the matrix the same, and if you make two rows of the matrix the same, then the determinant has to be 0. So anytime that you cross a vector with itself, you end up with the 0 vector. Okay, so natural question is, if you have, say, U here, let's say we have V here, and then we have W there, you're going to calculate out V cross W. You know it's going to be perpendicular to V and W, but you don't know whether it's going to be this vector pointing up or this vector pointing down. So is V cross W here going to point up or down? And the way to figure out whether it's pointing up or down is to use what's called a right-hand rule. So if you take your right hand, and so since we're doing V cross W, if you take your right hand, and so there's my right hand, I'm lying at along V. And if I'm doing it with my right hand, I'm going to position my right hand such that when I close my fingers, I'm going to close them towards W. So those are my fingers closing towards W. If I have my right hand positioned that way, such that when it's down lying along V and then it closes, it's going to close towards W, then my thumb is going to be pointed in the direction of V cross W. Then thumb is in direction of V cross W. On the other hand, if I had these oriented the other way, so if I had V is like this and W is like that, right? Well, then if I wanted to find V cross W, I'd lay my hand this way and my fingers curling in would have to be curling down. And the way to do that with my right hand means that my thumb would have to be pointing down. So there's my thumb. And so this means that V cross W would be going in this direction. Okay, so if you've done physics, there are a number of things, particularly in electricity and magnetism, that have right-hand rules. When you learn those, especially when you learn those before you know any multivariable calculus, that sort of that right-hand rule doesn't make a whole lot of sense. But now I can kind of tell you that the deep dark secret is that the way that right-hand rule works is they're really deep down. There's a cross product going on, translating that force. Okay, so if we think about this specifically in terms of our component vectors in 3-space. So remember, I is going down towards us, J is going to the right, K is going straight up. Well, so if I lay my hand down along J, so I can curl my fingers along I, curl my fingers towards J, my thumb's going to be pointing straight up. So I cross J is going to be equal to the K vector. If I swap them, if I did J cross I, my thumb would be pointing down, and so J cross I is negative K. The next one's a little bit easier to see. So if I lay my hand, take my right hand, point it in the direction of J, then my palm would be sort of facing up, my fingers pointing to the right. And then when I curl my fingers, they curl up. And so that's in the direction of K. And then which way is your thumb pointing then? Right towards you. And so that's in the direction of I. To do K cross I, I'd have my right palm facing forward towards me. So my palm is facing towards me. When I curl my fingers, they're coming out in the direction of I, and then my thumb is going in the direction of J. And so that's how the right-hand rule works. Okay, so let's talk about some applications of cross products. The first one we've already seen. The magnitude of the cross product is the area of the parallelogram with sides V and W. Right, and so we saw this before. If that's V, if that's W, we have a nice natural parallelogram by copying these over again. Okay. Okay, so V cross W is going to be the area of this, but we also can get the area by doing base times height. And so the base here is V, and this height here is W, that's not W, it's W minus the projection. So another way to think about that height is this height has to do with this angle right here. And so the length of the hypotenuse is the length of W, if theta is my angle here, then this height right here is going to be the hypotenuse times the sine of theta. So what this is telling me is that one way to get the area, which we figured out before, is do the magnitude of the cross product. That's V cross W. Another way to get this is to do base times height. And so when we do these, when we say these are both telling us the same thing, that's giving us a new formula. And so this is saying that the magnitude of the cross product is related to the product of the two magnitudes times the sine of the angle between them. Right? So the sine of the angle is telling us is related to the size of the cross product. And what's interesting about this, so remember the dot product is related to the cosine of the angle. And so remember, since it's related to the cosine's the biggest when the angle is small. Sine's the opposite. Sine's the biggest when the angles are perpendicular. Right? So to get the cross product as big as possible, you want the sides to be perpendicular. And so in terms of an area of a parallelogram, if V and W are perpendicular, that really gives us a rectangle. On the other hand, if the angle's small, if they're going in the same direction, then sine's going to be small, and the cross product's going to be smaller. So here's that formula nicely written. The magnitude of the cross product is equal to the product of the magnitudes times the sine of the angle between them. So another application is we can sort of take our parallelogram and add another dimension, and we get what's called a parallelepiped. So what a parallelepiped is if you have three vectors, u, v, and w, and then you keep adding them in to get a closed-in shape. So there's v again, there's u again, there's w again, some more w's. So it is the it's sort of, think about it sort of as a shifted cube, which you get by just keep adding putting the three vectors in to get a closed-in shape. This shape is what's called a parallelepiped. Okay, I'm not going to go through the derivation of this, but the volume of the parallelepiped is related to the cross product. And it is, so if you have u, v, and w in right-hand orientation, which is how we had it drawn there, you can get the volume of the parallelepiped is going to be u dot v cross w. Okay, and that's the same thing as doing the determinant, just a straight regular determinant where the first row, this u1, u2, u3, these are the components of u, v1, v2, v3, these are the components of v, and w1, w2, w3, these are the components of w. Okay, so this u dotted with v cross w, this is what's often called the triple scalar product. And if you understand determinants, this makes a lot of sense. So in 2x2 determinants, in some sense, geometrically, they're telling you about the area of generated by those two vectors. So if you do this in two space, if you have two vectors, you put their components into a matrix and you take their determinant, that's actually going to tell you about the area of the parallelogram in two space. So when you do this with three vectors in three space and take the determinant, that's going to tell you about a volume in three space. In this case, it's the volume of the parallelepiped. If you have four vectors in four space and you take the determinant, that's going to tell you about a hypervolume in four space. It's basically, this boils down to that determinants and tell you about volumes. And that is all I have for you right now. I will see you later.